Welcome to the Inquisitive Engineer. So this is a follow-up video to the video I did on calculating the immense forces that were acting on the Titan submersible at the depth of the Titanic. I have spent the last 2 weeks trying to find as much photo or video evidence on just how the Titan submersible was made instead of making some assumptions on my own. I was able to, and so I'm going to share my thoughts on the dangers of the design and why it likely had a catastrophic implosion. I'm not going to talk about the use of a game controller and other methods like that, and I'm also not going to talk about the viewport window in this video. But I am going to talk about the use of the dissimilar materials and the composite fiber that, as you may have heard in some of the media news, that those were two smoking guns in the poor design. So one concern about the design is the length of the design. Most deep sea vessels are made in a spherical design, but Stockton wanted to make it commercially viable to have many passengers on board to keep cost affordable, so he made it into a cylindrical design, and there are extra challenges and forces that you need to account for in those cases. So let's go to the whiteboard and discuss those forces. If I were to cut a sphere in half, no matter where I cut it in half, it is always a circle when I look at the cross section. So imagine if we have our pressure hull that has some wall thickness here. The water pressure is equally and uniformly pressing in on all sides. So that is squeezing the pressure vessel inwards. So how does the pressure vessel fight back and push back against the water? Well, if we visualize it and take some dashed lines out from the center, you'll see that this shape looks like a keystone where it is wider up on the top than it is on the bottom. And what that allows the pressure vessel to do is, say the water is pressing in on this keystone shape, because it's angled like this, it forces out on the neighboring sections of the pressure vessel. And if I keep going around and have that same view, every section of the sphere is that keystone wedge shape. So every section can push against the next section, which pushes against the next section. And that's what keeps the sphere from collapsing. In a sphere, again, this is true from all angles, no matter how I slice it. Now, if I make a tube like the Titan, what happens is they cut the sphere down the middle and then they stretched it like a limousine. So there's a half of the sphere, and there's a half of the sphere, and they put a composite tube in the middle. Now, the water pressure is still uniformly going to be pushing inward, but now something is different. If I go ahead and slice this down the middle, that composite tube is still going to have that cylindrical cross section with the keystones. But in the larger picture, what happens with all these forces? So the forces coming in, say, from the top in this example and coming up from the bottom cancel out in that compression of that circular cross section that we did before. But now the ends here are pushing in on a long straight section. In engineering, there's something we call about the buckling force of a column, and there's Euler's formula. And so, the water pressure is pushing in this way and pushing in this way, and it is squeezing the composite tube in the middle. So we can determine how much force is squeezing in on that cylinder. And all we need to do is know what the area of the circle is here and the area of the circle is here. And we know that the formula for the area of a circle is pi r squared. And in the previous video, we estimated that the diameter of the pressure vessel was probably 6 feet. So the radius would be 3 feet. And if I convert that to inches, area is pi times 36 squared. And that equals about 4,070 square inches. And in the previous video, we said that the pressure at that depth was roughly 5,400 psi. And we can multiply the 4070 by the 5,400. And we determine that the tube is getting squeezed on this side by 22 million pounds. And the tube is also getting squeezed on this side by 22 million pounds. So there's an extreme amount of force that is compressing on that carbon fiber center section. The second and most biggest concern of the design was the choice of using composite materials. And why was composites a bad choice? Well, as an engineer, when you're introduced to composites, you are typically using them in applications where you put the composites under tension. In the case of deep sea diving, you're actually putting the composites in compression. It's not the traditional way that composites are typically used. Why are composites typically only used in tension cases? Well, it revolves around the properties of the fiber itself. The fibers are typically carbon-based, and they're woven into strands of fabric, just like this shoelace. Maybe looks like a piece of linguine. It has a thin one way and a little bit wider the other way. And what you can go ahead and do is you can go ahead and wind it around a mandrel if I'm going to make a cylinder. And if I wind it around this way in what they call the hoop fashion, if I put pressure inside this can and pushing outward on this hoop section, essentially what it's doing is it's pulling on that carbon fiber like this. Now those carbon fibers can hold an extreme amount of force in tension, but if I try to push on it, it doesn't do much, does it? It can't hold up. So that's typically why you use carbon fiber and composite materials for tension-based applications. Now there are some other things you can do. Instead of also not only with the hoop to help take some other loads on a tube like that, you can go horizontally around like this, and then that helps with bending moments and keeping rigidity in the composite. Now, in the videos that I could find of the assembly of the Titan, I only saw them doing hoop wraps of fiber. I did not see them doing any horizontal along the length. I would hope that they did, but if not, that is also another potential of concern. So as you saw, when you make a cylinder out of a sphere, the pressure is pushing in on this side and the pressure is pushing in on this side, squeezing this together. Well, composites are just layer upon layer wrapped together through your thickness. We could think of it much like this phone book, where each layer of composite is like a page in the book. Well, what happens if I squeeze on these pages? as you can see, they're actually prone to separate. And that is one of the major concerns I have in the design of the Titan Submersible and why composite should have not been used. The final concern is over the bond joint between the titanium end caps and the composite center section. As you can see in these pictures, the end of the composite tube is machined down to mate in a groove in the titanium end sections. Well, how do you join titanium to composites? It's not like I have a piece of steel and another piece of steel and I'm welding them together. Well, the answer is that you just simply glue them together. And here you can see them mixing adhesive and applying adhesive by hand. Now this adhesive looks quite thick, and one of my major concerns here is just how sloppily they are applying it. And then as you squeeze the two pieces together, they are almost certainly capturing all kinds of air pockets in that adhesive at that bond joint. So if we go ahead and look at that bond joint, you have the carbon fiber tube like this with a little point machined in to mate with the titanium. And then you have the titanium section like this. And in between there, we had our adhesive. I'll do that here in red. So let's go ahead and label this the outside, and this is the inside. And again, the water pressure is going to be uniformly pressing down on the exterior of this pressure hull, squeezing inward. Now here's where concerns of dissimilar material come into play. The titanium over here is going to compress and react differently to the uniform water pressure on the outside than the carbon fiber. And for example, you have all titanium over here, all titanium here. Now all of a sudden, if you start going down through here, you're getting a little bit of titanium and a little bit of carbon fiber, a little bit of titanium, a little bit of carbon fiber. But then right here at the joint, there is a very sharp transition from titanium and carbon fiber to just carbon fiber. With this reacting differently to the pressure than the carbon fiber, likely one of these is going to be compressing more than the other half of that line. So that creates a shear stress along this boundary. And the shear stress for that composite is not good. In addition, that adhesive is going to react differently to the outside pressure than the titanium and the composite. And you're also going to end up getting shear stresses in that adhesive. So let's go ahead and clean that up and redraw it since it got a little bit busy there. So with repeated cyclings of that pressure, diving deep and compressing on these and putting shear forces in the composite right there, this very well could start delaminations in between the layers of the composite. And over time, these can grow with each cycle, and eventually they could get big enough where they might propagate into where this adhesive region was. Now there was likely lots of air inclusions in this adhesive, And possibly over time, some of those inclusions, also with the pressure cycling and possibly the shear stresses between the titanium and the composite, these also might have opened up into cracks. And with 5,400 psi of pressure out of here, it's very, very possible that water eventually leaked into the adhesive, and once it's there, if it can find a crack in the composite, it again can go through there. And once you have that fissure open and 5,400 psi trying to press it apart, this crack can just easily propagate down through the entire composite tube, and you would have a catastrophic failure. As I mentioned before in my previous video on the forces acting on the vessel, which the link is provided in the description if you want to go ahead and watch that video as well, any delamination, air pocket, or that sort of defect is very, very bad news, as that is a point where you can get a crack, and once the crack starts, it just propagates. In the previous video, I explained it in an example. If you've ever tried to open a bag of chips and you're struggling with all your might, you can't get that bag open, and you bite it with your teeth, and as soon as you make the tiniest little defect in that bag, it is extremely easy to peel open, and where you start that crack in that bag, it just propagates and propagates with so much ease. It happens in all kinds of materials. You know, here's a piece of aluminum foil, and without any hole in it, you can pull on it quite good and it will not separate. Now, if I take a knife and just poke a small hole in it, now if I pull on it, it doesn't take much force for that hole to create a crack, and then it splits right through that crack. And so there is a quick, simple analysis over the concerns of the design of the Titan. Between the extreme compressive forces providing buckling pressure on that composite tube from each end, and the shear forces between the titanium end section and the composite tube itself, that is setting up instances where you can go ahead and get delaminations in the composite tube over repeated stress cycles. Also, the manner in which they applied that adhesive to glue the titanium end caps to the composite midsection is just a poor way to do it. That certainly had to introduce air pockets, which over time, with that shear stress between the titanium and the composite, may have ultimately led to water seeping into the glue joint, and once it seeped into that glue joint, there was a location just inside there where the composite tube was ripe for delaminations, and the two may have met, and that let water go in and compromise the composite and hence the collapse. With all these concerns about using composites mixed with titanium, mixed with adhesive, because of all the dissimilar materials and the likelihood of having defects wound into the composite tube or at the glue selection, this is why the entire submersible community was just not in support of this design. You want to use one material, whether it is titanium or steel. At least we have very good history that you can melt them down and do a casting that is very sound. You can go ahead and test those in many ways to make sure that those metals are intact. And the entire pressure vessel itself is going to expand and contract in the same way. And we know that metals are both good in tension and compression. Unfortunately, Stockton Rush felt that he was a visionary and that he could do things better and likely cheaper. Unfortunately, he was trying to make this commercially viable, so there is a price point in mind to make it affordable for people to do such a thing. He obviously believed in his design and his vision because he was in the submersible every time it went down to the Titanic with other people on board. Unfortunately for him and his team that designed this sub, it wasn't very carefully and thoroughly thought out and the risks assessed. And it is very, very unfortunate that the general public had to suffer casualties. If you like this video, please like and subscribe. Go ahead and try to watch some of my other videos. I have all kinds of random, interesting videos that I am going to continue to upload. If you're a statistics person and like gambling, go ahead and check out the link in my description about just how astronomically crazy it would be to make the perfect NCAA bracket during March Madness.